I'd like to use the board a little bit today and just show you a super simple deployment of the tree rules. We're going to just run some very basic concepts and work on more complicated cases in a little bit. But for now, we'll take a look at disjunction and paths and how to read paths, how to find when paths close, when they're open, etc. We'll repeat a lot of this going forward with more complex cases, but for now let's look at a simple case. So let's take a look at a relatively simple example, and we'll use the tree rules and see how it goes. So we're going to compare what we do with the direct proof to what we have in the tree rules, and maybe finally we take a look at the truth table. So let's go ahead and do this. So we've got the following proof. Let's say you're trying to prove that if you've got P or Q and you've got not P, then you can conclude Q. So clearly that's disjunctive syllogism, obviously valid, etc. So how do we lay this out with the truth table? Well, with the truth table, remember, we would set it up in the following way. We'd convert the conjunction of the premises joined together with the conditional and the conclusion. We'd run the truth table for this, and we'd end up with everything coming out true here. T, 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 T. Okay, so given that you can believe me on that one, what do we do here for the tree rules? Super simple. We take the negation of the conclusion. So in this case, our conclusion is Q, so the negation is not Q. We take the negation of the conclusion as an assumed premise for the purpose of an indirect proof, or reductio. We're going to try to show that if we follow the tree rules, that all paths close. If all paths close, then that means that there's no possible way for all of these sentences to hold true together. If that's the case, then by reductio, we prove that if not Q can't be the case, then Q must be the case. Super simple. We apply the tree rules to all the complex formulas. There's only one, and that's P or Q. So if you want to, you could repeat P or Q, no need to. Split the paths at the operator, P in one path, Q in the other path. And now we've got a path with P, P or Q, not Q, not P, and P or Q. We've got another path that goes Q, P or Q, not Q, not P, P or Q. Okay, so if we look to see whether these paths close, what do we mean by the paths closing? We mean a contradiction appears in the path. We'll track back. Let's say on path number 1, we've got P, P or Q, that's not a contradiction. Not Q and P, that's not a contradiction. Not P and P, that is a contradiction. So we know that that path can't be the case. Let's look at the other path. You'll see that you've got not Q, P or Q, not Q, not P, and P or Q. Path closes. Game over. Okay, so what this means is that we've demonstrated that the negation of the conclusion, when combined with the negation of the conclusion here, when combined with the premises here, always leads to a conclusion, or can't be true. And then we say that by reductio, we've proven that the conclusion must follow from the premises. Okay, so once again, recall that we can do this with the truth table very simply. We could use the rules of inference. The rules of inference are very straightforward here. It's basically the use of, on line 1, P or Q, line 2, not P, and line 3, Q, by disjunctive syllogism from lines 1 and 3. Okay, so this is a premise. As we've seen, this is a premise, and this is the rule of inference. And so our method here is simply to, whoa, sorry about the glare. Our method here is simply to apply the rule of inference, and since we know that the rule of inference is good, won't lead us astray, that's a direct proof of the argument's validity. Okay, sorry about that glare. Okay, so that's a very simple case. We've got a disjunction and the negation of one of the disjuncts. We know that by the rule of disjunctive syllogism, that valid rule of inference, or that rule of inference allows us to show that Q follows directly. By contrast, what we did with the tree rules was we generated an indirect proof that Q. We generated an indirect proof that Q by showing that the negation of Q, not Q, always generates a contradiction. So by reductio, or by this indirect means, we show that the conclusion has to hold. So if the negation has to be false, then the only alternative is that the conclusion has to follow. Okay, so then finally we showed that treating the sentence as a whole, or the argument as a whole, as a sentence rather, where we take the conjunction of all the premises and then we join those to the conclusion with a horseshoe, treating the whole thing as a conditional statement with the premises as the antecedent and the conclusion as the consequent. When we set it up that way, we run the truth table and we show that it's a tautology. It has to be true. So that's the other option. So those are the three methods. So hopefully with this simple case, you're beginning to see the connection between the three methods.